Katie, Tom just sent me an email, so let me see what he needs.
Oh, great. I was just writing one.
Good morning.
Hi, Tom. Thanks for joining us.
Yeah, my apology. I think the Zoom link, it's a reminder, is the one for in 2 weeks. I was waiting on I think the Andrew Gettleman one, the one from Tracy's email.
I'm so sorry. Everybody's going to be, well, we'll see how it goes, but I'm glad you got in.
Yeah, no worries at all. Yeah, the link was just yeah, okay.
Yeah, thanks for letting us know, Tom. So I used the calendar invite. So Tracy, do you think we should send another quick email correcting that?
I will.
Okay.
The one is the calendar invite is the right one, and the one in the reminder leads to Andrew Gettleman's one,
Okay.
I think. Yeah. I'm gonna try quickly sharing my screen. Oh, would you mind enabling screen share?
You should be able to now. Tracy, stop sharing.
Perfect. Let's do this. Oh, actually, let me try something else. Maybe I'll do this. And then this. Okay.
Okay, that looks good. That's the full screen.
Perfect, thank you.
Yeah, we can just keep your screen up. I think I might wait just a few minutes just because of that mix up. We want to make sure we get everybody into the right Zoom.
Of course. The
So now you probably see the pop-up about the recording.
yeah, we can wait for a little bit. Just to make sure I calibrate the length of my talk properly. How long would you like me to speak? I can skip some sections depending on, if you want me to be 40 or 50 minutes.
That's a little bit up to you. I mean, we always like to have a good amount of time for questions. Usually people go about 45 to 50 minutes so that we have, 10 to 15 minutes for questions. So anything around that is great.
So does it exactly end at 11 if we start a little late, or should I think of it as ending as 11:05, or what is your preferred?
We can get started in like a minute, so we don't have to worry about that too much. But yeah, usually we end at noon Mountain, or I guess it's 11 your time.
Yeah, 11 PT, sorry, yeah.
Because people, do have other things to get to. But if there's still questions, like we can stick around a few minutes after that. That's no problem for me. Like if people still have questions after the end of the hour, that's fine.
Okay, no, I'll try to be mindful of time, and I'll accelerate to end around at the latest at 11:50 Mountain Time.
That sounds great. Yeah. Well, why don't we get started? I think people will just be trickling in. Hi, everyone. Sorry about, I think there was a little Zoom mix up this morning, so hopefully you all found the right link. But we're going to go ahead and get started. I'm really happy to introduce our CGD seminar speaker today, Dr. Tom Beucler. Dr. Beucler is an assistant project scientist in atmospheric science affiliated with the University of California, Irvine and Columbia University. As a recent update, he will be starting an assistant professorship in environmental data science at UNIL in Lausanne, Switzerland, and starting in August 2021. So congrats, Tom. He received his bachelor's of engineering and master's of science from École Polytechnique in Palaiseau, France, and his PhD in atmospheric science from MIT in 2019. During his PhD, he worked to better understand storms, radiation, and how they interact with atmospheric water in the tropics, and also received the MIT Rossby Award for Best Doctoral Thesis in 2019. He has presented at many conferences and workshops on the topic of machine learning and climate science, and currently serves as the co-organizer and moderator of the CLIVAR webinar series for emerging data science tools. His research combines statistics, theory, numerical simulations, and observational analyses to improve our understanding of meteorology and climate and guide the development of operational models of storms and clouds. Today, he will speak about atmospheric physics-guided machine learning towards physically consistent, data-driven, and interpretable models of convection. Tom, the floor is yours.
Well, thank you for the really wonderful introduction, and great thanks to the CGD Seminar Committee and UCAR for inviting me today and organizing this webinar. I would like to, first of all, thanks all my collaborators. There's way too many to list on the slides, and also, very importantly, all the administrative staff at UC Irvine and Columbia University, without whom this research would not be possible. So to start with an overview of my research, so I do work mostly at UC Irvine these days. I routinely collaborate with Columbia University and the DLR in Germany. And most of my work these days investigates how modern machine learning tools can improve climate modeling. I still work on how to better understand the tropical climate and extreme weather events. And I've been interested recently in how to better use atmospheric forecast to inform flood risk analysis and water management. As Katie kindly said, I'm more broadly interested in how modern data science tools can help analyze large to massive environmental data sets. And I've been co-leading a webinar series on the topic with US CLIVAR, and it's all available on YouTube, and we have a lot of very good talks. It's all open and free. I encourage everyone who's interested in the topic to check it out. Today, I will present some of my work on machine learning for climate modeling that investigates the more general question of how to best combine machine learning and physical knowledge. And more specifically, because that's my area of expertise, I will be focusing on data-driven models of atmospheric convection. And atmospheric convection can be broadly defined as the atmospheric motion driven by air density differences. And that often comes from the sun heating the surface, which results in less dense air that then ascends. That's exactly what's happening here. And this is a storm from the North American monsoon leading to a dust storm. And as convection form, as you can see, it interacts with radiation, with cloud, and then the storm will transport heat, water, and traces such as dust. Here you can see it vertically. And so atmospheric convection is responsible for fast vertical energy transfer between the surface, the atmosphere, and space. And for that reason, we really want to resolve the effect of convection and clouds on the climate in our models, because there are major constraints on climate sensitivity and other important variables we care for climate projections. And unfortunately, models mostly fail at representing the effect of fine-scale convection and turbulence on the climate, because climate models typically use a very coarse grid with empirical model of clouds, and that distorts the multi-scale interaction between climate, convection, and clouds. And this leads to very large uncertainties related to cloud in our projection of climate, and explain why clouds remain by a lot of different metrics, the primary source of uncertainty in our long-term climate projection. And that's the first motivation of this talk. The second motivation is that thanks to recent computational advances, we can now run global simulations that have a grid scale that is fine enough to explicitly simulate deep cloud system with horizontal grid scale of 1 to 3 kilometers, for example. But because of computational limits, we are only able to run such simulations for short periods of times, for instance, 1 year. And that's much, much less than the 100-year simulations we need to make long-term climate predictions. In parallel to the computational advances that led to the development of global cloud or storm resolving model, a lot of progress was made in a different field, stochastic optimization. And that has improved machine learning algorithm. And in this talk, I'll refer to machine learning generally to describe any algorithm that learns to perform a task from data without explicitly being programmed for said task. So these recent advances in computational capabilities and stochastic optimization have improved machine learning algorithm to the point where they can be trained on these high resolution simulations to accurately mimic the effect of deep cloud system on the climate. And that requires a bit of context. So in my research, I mostly relied on climate simulation that use a super parametrized community atmospheric model, where the multi-scale nature of atmospheric thermodynamics is explicitly represented via the combination on the left, an exterior model, which is almost identical to a traditional global climate model, and on the right, an interior model, which is an expensive cloud resolving model that explicitly represents the response of convection and fine scale turbulence to given large scale thermodynamic conditions. And then the job of the neural network is to emulate and replace the interior model, and that can accelerate the climate up to a factor 100 with very minimal accuracy trade-off. For those in the audience who are not familiar with neural network, which are also referred to as deep learning algorithm, if they have more than one layer, you can view neural network as very powerful nonlinear regression tools that take high dimensional inputs and nonlinear map them to high dimensional outputs. And then their free parameters are optimized using variations typically of the stochastic gradient descent algorithm that tries to minimize a loss or cost function that, if you're going for accuracy, typically measures how different the predicted output is from the output you're trying to learn from data. And neural networks have been very quickly adopted by the physical science community after the demonstrated success for both computer vision and natural language processing in computational science. So today I'm going to show you a lot of different neural networks, and the details of the neural networks can be adjusted for the modeling task at hand. But all of the neural networks I will show today take insolation, temperature, specific humidity, which is a water vapor mass concentration, and surface enthalpy fluxes as inputs. And then they output what we call subgrid scale thermodynamic fluxes. And that represent how unresolved clouds and turbulence redistribute heat and water vapor in height. For all of the models I'm presenting today, they also output radiative fluxes at the surface and the top of the atmosphere. And without further ado, here are the performance of such a neural network at emulating subgrid scale thermodynamics from a super parameterized climate simulation with Earth-like boundary condition. And the ground truth we're trying to simulate is at the top, and the neural network prediction is at the bottom. Convective moistening, so how you redistribute water vapor in height, is on the left, and convective heating is on the right. And what you can see, it's to first order, given the complexity of the task at hand, it's doing very, very well. It's doing so well that in the past years, some scientists this recent success have asked a very general and provocative question: can we eliminate physics entirely? And that can be rephrased as, can we avoid explicitly encoding physical knowledge in the algorithm we use to make atmospheric predictions? And another really provocative and very impressive results is from Wayne et al., and that is data-driven numerical weather prediction. And here you can look at a forecast which is a month ahead, which is of global temperature, and that is, it's performing impressively well a month ahead, and that's just using a neural network with a numerical integration scheme wrapped around it. And what the point I'm going to try to make today is that while the answer is maybe for initial conditions problem like numerical weather prediction, and I'm saying maybe while still keeping in mind that in the end you still need data to train the machine learning algorithm on, and that data mostly comes from a physical model in the end, so we never really eliminating physical models. The answer is probably no for climate modeling. And climate modeling is different. It's a boundary conditions problem where the physical system, Earth, is exposed to condition it has never been exposed to in the recent past. And the answer is no for at least 4 different problems I want to tackle today. Interpretability, physical consistency, ability to generalize outside of the training set, and sparsity of observations. And I'm going to explain each of these in the next slides. First, machine learning algorithms are typically hard to interpret. And because they're hard to interpret, they're hard to trust. So here I'm showing you emulated moistening on the left and heating on the right again, but this time it's in an aquaplanic setting. You can see it. And now we took our neural network after training it and we coupled it to a climate model, CAM here. And what you can see, and it's an example of why you shouldn't blindly trust a machine learning emulator, even if sometimes it looks good on the surface, is that it leads to the whole model crashing in less than a day. So why would you trust a machine learning algorithm if you don't even know if it's going to crash your climate model when you plug it back in? Now, the second problem is that machine learning algorithms typically violate conservation laws. So on the x-axis, I'm showing the leak, the residual from the mass conservation equation at the top, and the enthalpy. Also, I'm going to move this just in case it's preventing people from seeing the slides. So the residual from the mass conservation equation at the top and at the enthalpy conservation equation at the bottom, it's a squared residual, which is why it's in watts squared per meter 4. And I'm feeding a batch through the neural networks and calculating this residual. And if the neural network was perfectly conserving mass and enthalpy, what we would see here is it would be more or less a delta function at 0 watts squared per meter 4. However, when we feed a batch through it, we typically get this distribution of results. That's a histogram. And we can see that neural networks typically violate the mass and energy conservation laws by values that can exceed 100 watts squared per meter 4. And that's really problematic if we're trying to resolve the effect of top of atmospheric fluxes that our order may be 10 watts squared per meter 4 if squared or 20. The third problem is that machine learning algorithms typically fail to generalize out of the training set. So here I'm showing you a daily average sample from the tropics of a reference climate we trained several neural networks on. And this is the neural networks we trained on this reference called climate. And if you look at them, they're pretty good fits, especially given the complexity of the task at hand. You would deem these machine learning models good. And those include several machine learning model engineered to conserve mass and energy. I'll show that later. Now, if we take those machine learning algorithms and evaluate them in the deep tropics of an experiment that's 4 degrees warmer, suddenly they fail terribly. They produce those very unphysical peaks, and that's an error by a factor of, not quite 10, but more than 5. So definitely a deal breaker. And this is the central issue we want to tackle today. Now, the last issue arises when you take a step back from the modeling world. In the modeling world, the data is unlimited in practice to train neural networks because we can generate our own. For context, the neural networks we train for emulation purposes typically uses 40 million, if not 100 million samples during training, and that's not a problem because we can just run the climate simulations and output perfectly labeled data at arbitrarily high spatiotemporal frequency. And the global observing system can approximate the large-scale thermodynamic stand to some extent and inform the development of the climate model. Then we have a lot of good specific humidity and temperature observed data. But the same cannot be said for moistening and heating tendencies resulting from kilometric scale convection in clouds. Those are residual quantities, and usually they can only be accurately measured via very costly and targeted field campaigns. And as an example, here is the recent Eureka campaign in the Barbados that's shown on the left. And what that implies is that to design convective parametrization or subgrid scale thermodynamic parametrizations or subgrid scale parametrization in general, we have to work with very sparse and localized data, and that's a challenge. And so these four problems lead to the central question of this talk, is how can we make progress towards designing a model of convection that is data-driven but still physically consistent? And taking a step back, that relates to the much broader question that some of you may also be investigating in the audience, is how can we best combine machine learning and physical knowledge? And just to give a bit more context on this, this broader question really defines a subfield of physics-guided machine learning, which has really taken off in recent years, and it aims at adding physical structure to restrict machine learning output to only physically plausible solution. The idea being that the fewer degrees of freedom the model has to make its prediction, the less likely it is to be unphysical, assuming the structure you give it is close to the physical solutions. And there are several degrees to which we can impose a physical structure, and I think the most popular one in climate modeling by far, which a lot of you may already be doing, is to just learn the free parameters of a physical model whose structure is mostly fixed. And that guarantees a fair amount of control on the model's behavior and interpretability, but it comes at a cost, and the cost is to never be able to represent what's not already in the model's equations. So we may be missing phenomena that we can see in data just because they're not part of the possible solutions of our equations. Now, a slightly more flexible option that is also very popular in atmospheric science is to bias correct a physical model. So you learn a free-form bias correction to the output of a physical model. And that has been used very successfully for now almost 50 years to post-process numerical weather prediction models. So for example, model output statistics is a good example, if you're familiar with it, where you use a multilinear regression to correct the output of a meteorological model to make more accurate predictions based on local observations. And in this talk, I'm going to use an even more flexible approach where the model structure itself is for the most part machine learned to be as faithful to the data as possible. And physical knowledge is incorporated very intentionally to answer our initial question. And my talk will have four parts, addressing the four problems I mentioned earlier. And first, I will show that to gain trust in a model, you can tailor machine learning interpretability methods developed in computer science for the particular purpose of emulating physical processes. I'm also going to show you can enforce physical constraints approximately in the loss function or exactly in the by changing the architecture of a machine learning algorithm to make machine learning algorithm more physically consistent. Third, I will show that you can help neural networks or generally machine learning algorithms generalize to unseen data by physically rescaling their inputs and their outputs. And finally, I'm going to show preliminary results suggesting that rescaled machine learning algorithms learn more general mapping and may facilitate transfer learning. And note that while I am investigating the specific case of deep learning parametrization of subgrid scale thermodynamics for climate modeling, the framework I'm presenting today and the four problems I enumerated earlier are general enough to be applied more broadly to machine learning emulation of physical models in general. So for example, meteorological models and oceanic models. So starting with the interpretability challenge, interpretability is commonly defined as the degree to which a human can understand the cause of a decision. But for our purpose, we can define interpretability as the degree to which a human can consistently predict a climate model's result, or the result of a machine learning algorithm trying to emulate a process in a climate model. And today I will introduce two interpretability methods that were developed in computer science, or computational science more generally, and that greatly increased our confidence in the neural network's prediction. And I'm showing how you can tailor them to the particular case of parametrizing convection. The first technique is called partial dependence plot, and it it shows the marginal effect of one or two inputs on the predicted outputs. And very plainly, and without going into the mathematical detail, the partial dependence function is just estimated by averaging the model's prediction over chunks of data with similar inputs of interest. So it's just checking that the output is consistent with a physical intuition by conditionally averaging over one or two inputs we choose that we know control the model's output or should control it based on observations and physics. And without further ado, I'm going to show partial dependence plots based on two quantities we know are reasonably good proxies for the occurrence and intensity of deep atmospheric convection. So the first quantity is going to be mid-tropospheric moisture, which I will abbreviate as QM, and that's the amount of water vapor at 500 hectopascal, just a few kilometers above your head, and you can see that as fuel for convection and storms. And the second proxy I'm going to show today, the second input, is called lower tropospheric stability, LTS, and that's a reasonably good proxy to know if the air at the top of the boundary layer is going to be buoyant enough to ascend and result in deep atmospheric convection. So it's going to control the occurrence and intensity of deep convection. So now I'm going to show results on the left-hand side is the vertical profile of subgrid moistening, how water vapor is redistributed in height, and on the right-hand side, how temperature is distributed in height. And I'm going to first fix LTS and very mid-tropospheric moisture. So what we're going to be looking at is the general structure of these moistening and heating profile as we increase mid-tropospheric moisture. And what we can see is that when mid-tropospheric moisture reaches relatively high value, we can see that convection is already doing a lot of, we see a lot of drying and a lot of heating. And that's a signature of deep atmospheric convection. Because as convection occurs, as the air ascends, water vapor is going to condense into liquid and ice water, and that's going to result in a drying of the profile. And then as water molecules lose energy by going from the vapor phase to the liquid and solid phase, this energy is going to be transferred in the form of heat, and we're going to see heating here on the right. So that's the signature of deep convection and storms occurring. And we can keep playing this game and increase mid-tropospheric moisture. Then we fix mid-tropospheric moisture so that there's a lot of fuels, there's a lot of water vapor to be condensed. Now we're going to decrease lower tropospheric, now we're going to increase lower tropospheric stability to see if, as we expect, it damps convection. And we can see that the more lower tropospheric stability we have, the less intense convection is going to be. And here I'm describing convection, but really we're looking at the output of the machine learning models. And so here what we're checking in the end is that the machine learning model behaves as our physical intuition and what we learned from observations would dictate it should behave like. And that's already a way to gain trust that a machine learning algorithm is not outputting something completely unphysical. The second method I'm going to introduce today, that was an interpretability method that was really helpful in our case, is called Saliency Map, which is defined as a squared Jacobian of the emulated mapping. And in computer vision, it's very useful to understand why a neural network makes a given prediction. So here we have a neural network tasked with identifying whether this is an owl or not, a binary prediction. And what you can see is that the gradients that's going to affect this prediction the most are around the eyes of the owl and the forehead of the owl. So if I were to blur these parts of the image, I could try to fool the neural networks and make it predict that there's no owl. So if I change these eyes and this forehead, that's what the algorithm is looking at to make the prediction. And this is related to the Jacobian of the mapping we're trying to emulate, which is the sensitivity of the output of the algorithm to the input of the algorithm at a given input. And the reason this interpretability method is well adapted to deep learning and neural networks is that deep learning libraries calculate this Jacobian very efficiently because it's the same Jacobian that is used to optimize the free parameter of the neural network. And so years and years and years of work have been done to make sure this was calculated very efficiently. So you can output it as just a fraction of a second once your neural network is fit. And in our case, it reveals the linear response of convection. So it's the sensitivity of convective moistening to specific humidity. So sorry, our mapping is much higher dimensional, but we can extract a lot of useful linear relationship from it. And that's the first one we can extract from the first outputs and the first inputs. And this is how it looks. So on the y-axis is the response of convective moistening, so how convection redistribute water vapor in height following water vapor perturbations at different level. And there's a lot you can learn about the neural network. And assuming the neural network is a good fit, there's a lot you can learn about your atmospheric data set just by looking at this Jacobian. It's very rich in information. So for example, if I read the blue diagonal of this matrix, what that means is that if I add, for example, water vapor at 500 hectopascal, it's going to be removed by convection. It's going to remove local anomalies in water. And it's going to redistribute it in the lower atmosphere by reducing the drying below. And here I want to take a few steps back because this is really the particular case of convection, but what's really cool here is that we obtained this in a fraction of a second. If you wanted to obtain this in a normal, more traditional, even climate model that's not that doesn't use machine learning, it would take 100 of a forward perturbation experiment to get some signal over the noise. Or it would require calculating the entire adjoint of your model, which is extremely time-consuming and sometimes not possible. And in addition to helping with interpretability, these linear response functions can also help with stability. And I'm going to quickly show you how. Here are two neural networks. On the left, it's a pretty well-tuned neural networks. That's its linear response function. On the right, it's one that was calculated more quickly. It wasn't necessarily well-tuned. You can see it doesn't damp moisture enough with convection. And I don't know which one is going to crash the climate model, but what I can do offline without even coupling it to the climate model is couple it to simple two-dimensional dynamics. And this was work in collaboration with Noah Brenovich and Chris Bretherton at the University of Washington. And so that's Noah Brenovich developed the code that allows you to code it to a simple dynamical model. And then you get a full stability diagram with the growth rate on the y-axis, that's amplification and that's damping for each mode of horizontal variability. And what you can see is that for the network on the right, there's a lot of unstable modes that are spurious, whereas all you should get is gravity waves that propagate and damp and are damped. And so without even coupling it to the climate model, you can already guess the neural networks to the right is going to be unstable and the neural network to the left is going to be stable. And then by using this tool, we were able to develop strategies to fully stabilize neural networks offline, both for the super parameterized model that we did, and then for the UW team, the global cloud resolving, the machine learning parametrization of the global cloud resolving model they developed. And then when coupled back to the climate model, both models were able to run without crashing for more than 1 month. So this was a really fun project, but I again wanted to take a few steps back here, and the reason I started with this section for this talk is that I think it's really important to gain trust and understanding if you're trying to use machine learning for climate modeling purposes, where trust is so important, both for the climate modelers, but also to communicate the information to the public. We have a lot of different physical techniques, and computer scientists have developed a lot of machine learning interpretability techniques, and combining both can really help you gain a lot of trust and make those black box that are everyone calls them black box, but if you spend a lot of time analyzing them like that, they are in the end quite interpretable, at least from a high level perspective. And this is in an article we published in the Journal of Atmospheric Science, Brnovich et al. Last year, and I invite you to check it out if you're interested in all the details. Now, coming back to the first problem motivating this talk, I'm going to ask, how can we enforce physical constraints in data-driven models of convection? And in our case, I will propose solutions applied to the conservation of mass, energy, and radiation in neural networks. And I'm using neural networks because they have very high representation power. And I care about conservation of mass, energy, and radiation because that's the conservation laws you care about enforcing when you're parametrizing subgrid scale thermodynamics in a climate model. However, the methods and the framework I'm going to show apply to any physical constraints you can write down analytically for any machine learning algorithm emulating a physical system. So the first option, the way to enforce conservation laws in the machine learning algorithm, and the one that's very common in the literature, is just to add a term in the loss function of your machine learning algorithm. And that term is a penalty for violating conservation laws. And it's very similar to Lagrange multipliers. What you do is, if you have your initial loss function, here it's the mean squared error because I care about accuracy. I'm only going to reserve part of the loss function for the mean squared error, and I'm going to add a part that punishes the machine learning algorithm if it violates conservation laws by too large of an amount. The problem is that this is only approximate since you're just trying to minimize the loss function, and sometimes as climate modelers, we just don't want to tolerate any mass or energy leak because we don't want to accumulate a leak at each time step if we're going to integrate our climate model simulation for 100 years. And so that encourages us to develop a more novel technique. And I'm going to show that by adding constraint layers, we can enforce conservation laws to within machine precision, within neural networks, or machine learning algorithm. And for those of you interested in details, the way you do this is you start with this, imagine you start with a standard neural networks. It has M inputs and it maps them to P outputs. But now you have N constraints, so conservation laws, for example. And so instead of outputting P outputs, you're just going to output P minus N outputs. And those we're going to call the direct outputs. And then you're going to use what we call constraints layers that are fixed layers that encode conservation laws to exactly calculate the remaining outputs so as to exactly enforce conservation laws. And so far, this in itself is not very original. It's just using residuals to enforce conservation laws. But what was novel is that we coded this within the neural networks, within the machine learning algorithm, so that we then concatenate the direct and the residual outputs inside the neural networks, so that when the neural network is optimized, the conservation laws are exactly satisfied. So what that means is that the gradients of the loss function are passed through the fixed constraints layers. And so the final weights and biases, the free parameters of your machine learning algorithm, will be informed by the constraints you coded here. And now onto the results. First, if we do it using the first option, the loss function, I'm going to show you there's a trade-off between performance and enforcing physical constraints. So on the y-axis, I'm showing you different components on the loss function. I'm going to start with the mean squared error that represents the performance of the machine learning algorithm. And so since it's a loss, up is worse and down is better. We're trying to go as low as possible in this graph, which uses a logarithmic scale. This is the mean squared error for an unconstrained neural network. And this is the mean squared error for a corresponding multiple linear regression. So here we can make a first observation that a neural network performs better than the multilinear regression baseline. That is very reassuring. And that means that that is very reassuring for the purpose of using neural networks. It means that we use the right algorithm for the right purpose. Our problem deserves to be treated non-linearly. If it was the opposite, you may as well just use a multilinear regression. And now, despite the neural networks performing better, it's violating mass and energy conservation laws by a much larger amount than the multilinear regression is. And that's really worrying. So if we increase in the loss functions the weight given to the penalty for violating conservation laws, as expected, as we increase the weight, the neural network follows conservation laws more and more closely, but that comes at a cost since the loss function is broken in two, and the cost is performance. It performs worse and worse. Meanwhile, if we enforce constraints by changing the architecture of the neural network, we get competitive performance and we get a really, really, really tiny mass and energy leak. So we were really happy with that. These techniques, by changing the architecture, we can enforce constraints, and that is valid for any physical constraints as long as you can write it analytically. We have an article now published in Physical Review Letters detailing how to do it with any generic model. You can enforce these constraints exactly, and you can still maintain competitive performance and still build a data-driven model. Now I'm going to switch to the next problem of the talk, is that even when physically constrained, the neural networks still fail to generalize, as I showed you when you go from a cold to a warm climate, for example. And that's really a challenge I've been fascinated by in the last 2 years and spent probably most of my research times in the past 2 years working on. And our first ideas when we identify this failure mode is to make it even more apparent, because we wanted to find the minimal set of solutions to help neural networks generalize better between climates of different, for example, surface temperatures. And so our idea was to break the model even more, so that we clearly know which solutions work and which solutions do not work. So I'm going to design a generalization experiment on purpose to break machine learning models. I'm going to train and validate our machine learning models on a cold aquaplanet simulation. Then I'm going to test them on a warm aquaplanet simulation. That's whose surface is 8 Kelvin warmer than the cold aquaplanet simulation. For this aquaplanet simulation, the surface temperature is prescribed as a function of latitude using a realistic equator to pole surface temperature decrease. And this is what the warmer experiment looked like. And what you can see here, I'm showing the maximal surface temperature as a function of latitude with a dotted line, is that there's an entire, there's an entire set of latitudes where the neural network is going to be exposed to surface temperature it has never been trained on. And that's where we expect it to fail. So it's trained on the cold climate, and it's tested on the warm climate, and particularly in the deep tropics of the warm climate where we know it's going to fail. And I'm going to show you the failure mode. It's very dramatic. Again, we take daily mean tropical prediction in the cold climate. We take a neural network that's a good fit. And here I'm going to use the word brute force to describe a neural network that's just a standard one. I'm not using any physical trick on it. I'm just fitting it, and it's a good fit in the cold climate. And now I'm testing it in the warm climate, and it fails miserably. It fails even more miserably than when we tested it in the plus 4 Kelvin climate. This is failing by a factor of not quite 100, but more than 20. That's gigantic. That's a failure you would never tolerate in a statistical emulator. And the question is now, how are we going to proceed? Can we make simple modification to a machine learning algorithm so that it generalizes much better? And the idea we borrowed from the idea of self-similarity in fluid dynamics is that we can physically rescale the data to convert an extrapolation problem, which is causing the problem when we try to generalize, into an interpolation problem by changing the input and the output variables of a mapping. So here I'm writing a mapping in the mathematical form, and you can see that the neural network is trying to fit the function going from the input, which are the large scale thermodynamic state of the climate model, to the output. And what I've just shown you is that if I take a brute force mapping, this function is not climate invariant. This function is different in the cold and in the warm climate. So if you calculate that function in the cold climate using data, then it's going to fail in the warm climate. So the idea is that this some degree of self-similarity in our data so that we can find a rescaling for the input and the output variable so that function is as close as possible in the cold and the warm climate. And that should really decrease our generalization error. Now the question becomes, how do we choose such a physical rescaling? And from a statistical perspective, I'm gonna approach it with a statistical perspective, just because it's easier to visualize. And I'm going to start with the first input of our machine learning model, which is specific humidity. And because of Clausius Clapeyron's, the specific humidity is clearly out of sample in the warm climate. You can see it here by looking at the logarithm of the histogram. But through the Clausius-Clapeyron equation, we know that there's an upper bound to that specific humidity, which is dictated by how the saturation pressure of water vapor evolves as a function of temperature and pressure. And so if we normalize specific humidity by the saturation specific humidity, we get relative humidity. And then we take into account this increase from a cold to a warm climate, and we get inputs whose distribution vary much less between the cold and the warm climate. And just because I lack time, I'm gonna skip over this. The message for those of you who are more interested in how you do it in practice and the algorithm is then you can code these rescaling as layers, or you can code them as part of your data generator, so you don't have to duplicate your training validation test data set every time you try a rescaling. And you can test the rescaling quickly using very simple algorithm like multilinear regression, and then you just keep the rescaling that yields the best generalization. But for the scaling I just showed you, the specific humidity one, just switching from specific to relative humidity already improves the generalization abilities dramatically. And here it is for the difference in the distribution for specific humidity at a given level versus relative humidity, where the distributions are much more aligned. You don't have to extrapolate in that entire range. And you can play the same game for the other inputs. We found that the best rescaling for temperature was a version of plume buoyancy. And so again, this one, instead of normalizing, you can think of this rescaling as most of our generalization errors in climate problems, at least when you're doing subgrid scale thermodynamics, come from the thermodynamic component, because quantities related to water, so for example, saturation, vapor pressure, the saturation vapor pressure increase a lot with climate, but then dynamical quantities, we can expect them to change much less with climate. So by going from temperature, which clearly is going to be out in sample in a warm climate, to buoyancy, which is an acceleration, the dynamical quantity in meter per second square, we're much less likely to be out of sample. And similarly, latent heat flux tend to be out of sample. And here I'm wondering if this is the top plot is probably wrong. You get so sorry, that's the wrong distribution. I think I plot two different rescalings here, but latent heat flux will be clearly out of sample in the warm climate. But when you normalize it using the near surface moisture disequilibrium, the two distributions align much more, because you only left with quantities that depend on the exchange coefficient and the wind, and those are much less likely to change with climate. Okay, and I'm going to be out of time if I talk about the fourth problem, but the bottom line is that the climate invariant rescaling I just showed you allows you to design neural networks that can be trained on an aquaplanet simulation and or linear regression that can be trained on an aquaplanet simulation and perform much better in an Earth-like simulation. And so they also help you transfer across different regimes, not just across different climates. And I'm happy to go into more details for those of you who are interested. And now, just before I move onto the overall conclusion, a lot of the work I presented above was about incorporating physics into machine learning models of convection. to make data-driven models of climate processes more consistent with what we know from physics and observations. But another exciting scientific endeavor where machine learning is also really powerful is to go the other way around and extract physical knowledge from data using machine learning. And that can be done for the problem I just showed you. So for example, if I trained a linear regression in a cold climate, then I trained the same on the warm climate, and here I'm showing you the brute force regression I talked about. So it's just out of the box, and it fails. It fails as going from cold to warm and at going from warm to cold. And you can just look at the differences between, for example, the coefficients of the multilinear regression and understand why it fails. And you can understand why a lot of the statistical models we would fit in our reference climate would not be valid for a warmer climate. And in our case, for example, linked to convection, a lot of it is linked to the upwards shift of the atmosphere with warming, where, for example, the tropopause, and so the region of the upper troposphere where convection is damped if you add water vapor, moves upwards with climate. And that you cannot describe if you stay in physical space. So by going from specific humidity to convective moistening, but then if you make it climate invariant, it automatically scales this, and then you get mappings that if you train them on a warm and a cold climate are much more similar. Now, still on the topic of convection, but going more on the dynamical side, I also wanted to show you an unsupervised machine learning example, so where you don't need labels, or at least there's much less human intervention in how you design and how you use your machine learning algorithm. And I'm showing work from Griffin, who's a PhD student at the University of California, Irvine. I'm very lucky to work with. And he's interested in the provocative question I asked at the very beginning of the talk. So how much can we learn from the atmosphere, for example, from a purely data-driven approach? So that is almost exclusively without human intervention. And he built he builds this latent space that summarizes very complex, high-resolution cloud resolving vertical velocity data using a statistically constrained variational autoencoders. And what it does is that it automatically identifies different types of convective regimes and separates them in this three-dimensional latent space in a way that's much closer to what a human would do than if you just use standard methods like linear approaches or principal component analysis, where these methods just focus on the modes of maximal variance. So they just tend to look at deep convection only, because that's what creates the largest pixel to pixel variance, and then they'll just tell you whether the deep convective cluster is on the left or the right. But these unsupervised learning techniques, because they loss function normalize different modes of variance, can automatically identify without human intervention a lot of different convective regimes. So non-convective, shallow to deep, detrained deep convection, weak convection, with barely any human intervention, except labeling the different clusters at the end so that they have humanly interpretable names. And then, as Katie said, a little bit, a short announcement that I'll be moving away from the University of California, Irvine, and I'll be moving on to a assistant professorship in environmental data science at the University of Lausanne in Switzerland. And I'll be soon recruiting 2 PhD students and 1 postdoc. The job ad should come in the next month to work at the intersection of tropical meteorology and machine learning. And so to conclude, I showed in this talk that we can tailor machine learning interpretability methods for the particular purpose of emulating physical processes. We can enforce physical constraints so that a machine learning algorithm or generally statistical models are more conform to the laws of physics. We can do it approximately by changing the loss or cost function, or exactly by modifying the architecture. We can help neural networks or multilinear regression, any kind of statistical model, better generalize to unseen condition by physically rescaling the inputs and the outputs of that regression, to better take into account, for example, the self-similarity properties in our data set and what we know about how the climate is going to change. And then these rescale machine learning algorithms learn more general mapping and facilitate transfer learning, not only across climates, but also across different types of data sets. So for example, idealize and Earth-like models or Earth-like models and observations. And that's really exciting because that means that those climate-invariant neural network may be a promising tool for assimilating data from, for example, sparse observational data from field campaign inside climate models in a way that's physically consistent. Not necessarily replace data assimilation, but at least assists data assimilation. And with that, thank you again for inviting me today, and thanks to all of you who stayed until the end of a long seminar day. And I would like to reiterate my thanks to all the co-authors of this work, and I make my code and articles open and reproducible using Archive, GitHub, GitLab, and I encourage you to check out my website or email me directly if you have any questions on my work. Thank you.
Thanks very much, Tom, for a very nice talk. Lots of interesting details to think about. As always, if you have questions for Tom, you can type them in the chat and I'll read them out loud. You can use the Zoom raise hand feature and ask your question out loud. Looks like we have a question from Seth in the chat. Great talk. Do you have any thoughts about how to apply physical rescaling and climate invariance in the vicinity of important fixed points like the freezing point of water?
That's a really good question. Okay. That's actually something we thought about, and I don't think we have conclusive results yet. Okay, so am I still sharing the bottom screen? Can you see my slides here?
Yeah, they just popped back up. It's not full screen, but we can see the PowerPoint.
Okay, perfect. Okay, so I'm going to try to go back to this slide. Yeah. Although, well, maybe I'll go full screen again. Sorry, this is okay. So here I put little tildes on the vertical coordinate as well. And for example, when I think of freezing points, I'm thinking of aspects in the vertical profiles of the quantity we care about that may depend more on temperature than pressure, for example. And what you could do is you could rescale the vertical coordinates, knowing that there are invariants regarding to, for example, a fixed. For example, if you're talking about a freezing point more at a fixed temperature than a fixed pressure. And so what you could do is you could redesign your vertical coordinate to take into account that invariance and then create models that automatically scale with respect to that freezing point. And then I think that answers part of your question, and maybe another part would be you can still use some versions of the Clausius-Clapeyron equation to, for example, take into account microphysical knowledge, a knowledge of how microphysics are expected to change with climate to make you model to help you model better generalize across climates. I'm not going to hide that rescaling inputs and outputs is relatively straightforward in algorithmically, but rescaling your vertical coordinates is much harder. And that's why we still don't necessarily have conclusive result on that exact topic. But yeah, I'd be interested to talk. Does that address your question, or maybe that's a little bit too detailed?
Yeah, he says thanks in the chat. So bunch of raised hands. So we'll start with Bill Large. Go ahead.
Yes, thanks for a very informative talk, and it's very reassuring to see such work going on. But I wanted to get on to the issue of vectors. Most of your things you were discussing are scalar quantities. So if in a convection algorithm you put in the horizontal components of flow, do the schemes actually figure out that it's the convergence that matters, or do you come out better if you put it in as a convergence?
So in our particular case, and it's not a general rule, the horizontal velocity did not really help. But that's also because of the some of the awkwardness of the superparametrized setup, where, for example, I don't know if you're familiar with it, but because we explicitly enforce scale separation at the climate modeling stage, you don't necessarily communicate the momentum fluxes properly between the large scale and the small scale. In general, I would expect quantities like convergence, but for our case, it would be convergence. So it would be a mixed dynamic thermodynamic quantity. I'm assuming convergence of moisture and temperature would probably help as inputs if you were repeating this exercise on a global climate model. And I think you're also getting to the interesting point. So with the parametrization we design, it's a vector. So it's in that sense, we're taking an atmospheric column and we're mapping it back to an atmospheric column. And as you said, you're losing information in the process, right? Technically, you also want to know a little bit about a neighboring column. And so a way of doing that would be to go from an artificial neural network like we have to one that has a larger input, or a convolutional neural network that would naturally take into account some of the horizontal information around your atmospheric column. But in a recent paper we wrote in an Earth-like simulation, going from column to column actually gives you very good accuracy, and taking into account neighboring column is too computationally expensive to be worth it in our case. Does that address your question? That doesn't mean it's true. Like for more dynamical quantities, I'm expecting having neighboring column is really helpful. And if you look at papers about machine learning parametrization of boundary layer turbulence, then having neighboring points is really helpful in the horizontal. For example, if you're trying to replace a smag risking scheme. Yeah.
Great.
Great. Dan, go ahead.
Hey, Tom, thanks for a great talk. I had a question about this slide you had where you were showing the progression of the loss function as you're increasing the sort of weight, the soft constraint on the physical constraints, and all of a sudden it like goes, you know, when you impose this new structure, suddenly you're able to like both meet your data constraints and you know, meet the physics. And I guess like that discontinuity was a little bit surprising. I'm wondering, like, and you're saying it's because you're changing the architecture of the model.
Yeah, so it's that does not go. Yeah, sorry, it shouldn't be a discontinuity. Technically, that's just to clarify, that's a loss function. It goes from 0 to 1, and that's like a completely different way of doing things. So I'm putting it on the right, but it's not technically a discontinuity. But sorry, I'll let you finish the question.
Yeah, I guess like broadly, I was wondering if there are some like downsides. You know, is there a greater risk of overtuning this model or something? You know, what's different about this model that lets you do this, and are there any downsides?
Yeah, so sorry, I should have let you finish your question first. That's a really good question, and it's so just to clarify, this is a function of the conservation weight. So we have continuity as we vary the conservation weight here, and then this, you know, they should be almost like a blank column here, and that's like the completely different method where we completely change the architecture of the neural network, and you're asking about the trade-offs. Because like there's no free lunch, right? So we always think that when we gain something, so obviously there must be a cost, and it's true in my case. So it's not true in idealized fluid dynamics and applied mathematical applications that have tried to do this. In their case, because their problem is low dimensional, they always gain things because, I don't know, if your system is 5-dimensional and you have 3 constraints and you're giving so much information by giving it the constraint that you gain in everything. You gain in generalization ability. It's easier to train. You need less data. But what we find is it's really interesting is in climate modeling, that's not true. In my case, the problem is, you know, I used inputs that are dimension 300, outputs are dimension also like 200 or 250. I only have 4 constraints. So clearly I'm not necessarily helping the mapping. And so it's harder to train. So it takes a bit longer to train. And then in terms of accuracy, I have 150 here, but I think the best models here is like probably 148 or something. So there's like a tiny accuracy trade-off. So it's a little harder to train. It's not trivial to implement. You usually have to use a different optimizer because it's a little bit harder to optimize. But if you're careful about it, we managed to get almost as good of a performance as the brute force model. And then the constraints, there's no comparison. It's just amazing. You do it within machine precision just because you built it in TensorFlow. You wrote it in TensorFlow to make sure the residual was close to 0, or TensorFlow, PyTorch, however you like to write your machine learning models. So yeah, that's a trade-off. There is a trade-off. You're right.
Deepak, go ahead.
Hi, Tom. Thanks for that great talk. I have a question about your rescaling, and you mentioned self-similarity.
Yeah.
And so in fluid dynamics, we usually rescale by non-dimensionalization.
Yeah.
But I noticed that you were, it's like temperature to buoyancy, for example, is dimensional to dimensional. So I was just wondering if you thought there was any advantages or disadvantages to, take all your input parameters and try and find a few non-dimensional parameters in there.
Yeah. So, according to the Buckingham pi theorem, right, in self-similarity, the first step is to form the right number of non-dimensional parameters and then rescaling it. But in the end, when you just think about data, it doesn't really matter which, you could units don't matter as much as how much you change the distribution, because you could very much think of devising your data by its unit. You get something dimensionless, you didn't change anything, right? So I think in the Buckingham pi theorem, you make them dimensionless, but there's something deeper going on. You use that rescaling to find numbers whose distribution is a little bit different and produce a more general model. And I think if you write it down like that, you get something that's dimension. So for example, relative humidity is dimensionless. You divide specific humidity. Well, specific humidity is already kilogram per kilogram, but you divide kilogram per kilogram by kilogram per kilogram, and you get something that's dimensionless. Now I'm trying to see how to properly answer this question. You can always, when I write my paper, especially for physicists, I can always make quantities non-dimensional in the end. But when you're looking at data, it's really not the units that matter, it's the nature of the distribution. And I think in fluid dynamics, people do both at once. I think they manage to get non-dimensional numbers and the distributions align.
Yeah,
so
that's
in
what I
the
was
end,
going to
it's the
bring up.
distribution part that matters for the mapping, yeah.
Yeah, so that's what I was going to bring up is yes, you can always non-dimensionalize with dividing by a unit, but you don't,
Yeah.
right? We divide by
Exactly, right? So
quantities.
there's something much deeper going on when we use that theorem and make non-dimensional. And so that's what I'm trying to explore. And it's a little tough, but because in atmospheric thermodynamics, it's super high dimensional and much messier. So there's a little bit of trial and error. But in general, our rule is try to replace thermodynamics with dynamics, because dynamics vary much less with climate than thermodynamics. And they vary a little bit, but you can hope that the neural network did learn that small variations in the complex data set. So some results I didn't show is, for example, if you train it on an Earth-like simulation rather than an aquaplanet simulation, it's going to learn a lot of relationship that help it generalize a bit better. Because it's going to see more variety in the regimes. For example, land versus ocean, it gets to see more diversity in convective regimes. So you generalize already better. So you're hoping that in the dynamical realm, it can generalize well already. And then for thermodynamics, you just scale by things that you know how they vary in climate. So like Clausius Clapeyron equation, we know it holds. We know specific humidity is going to roughly vary exponentially as we increase temperature. So you divide by it. And then you're more similar to what you would do in fluid dynamics. That's just give you a dimensionless number. Yeah, sorry, that's not a complete answer, but I'm still myself trying to explore. I still haven't fully written this up. I'm trying to explore the full links to self-similarity, and I'd be super interested to hear about your thoughts, maybe after the talk.
Yep, thank you.
Great, thanks everybody. Thanks for the questions. I think we'll wrap up there since we're a little over. Thanks so much, Tom, for a really nice talk. Next week, we will hear from Anna Deppenmeyer of NCAR